Mr. Gucci here with a help video for problem number 9 where things get interesante. In order to combust 2.864 grams of pure octane, that's gasoline, that's this thing C8H18 right here, all right? In order to combust that many grams of pure octane, how many liters of oxygen gas are needed? Assume that the gas is at STP. So I have a hint here, all right? This starts off like a normal stoichiometry problem in which you have 2.864 grams of pure gasoline trying to figure out how much oxygen is needed. So we're going to start this off as a standard stoichiometry problem, all right? So I'm going to go to my worksheet. Let's do Abington Maroon, all right? Problem number 9. So we have got 2.864 grams of gasoline, all right? We need to figure out ultimately how many liters of oxygen gas are needed. So let's just get started with the stoichiometry. Next thing we're going to do to convert from grams into moles, we are going to divide by the molar mass of gasoline. That's the molar mass of C8H18. So I'm going to go to Google and I'm going to Google C8H18 molar mass. And I get 114.23 AMU. That's the molar mass of gasoline. That's what you get when you add together 8 carbons and 18 hydrogens from the periodic table. All right, next up, we need a mole ratio conversion. So we are getting out of gasoline and into O2, oxygen gas. Let me go back to that worksheet and see what is the balanced equation. It says here, for every 2 gasoline molecules we burn, we also consume 25 oxygens. So for every 2 gases we burn, we also consume 25 oxygen. So let's take a look at our steps here. All right. In this problem so far, we've gone from grams of gas, all right, into moles of gas, all right, and now into moles of oxygen. Now at this point, you would think that you would multiply by the molar mass of O2, multiply by 32.00 AMU. But that is wrong because this problem does not want to get an answer in grams. It wants an answer in liters. So what I'm going to do right now is I'm just going to hit equal. And I'm going to figure out how many moles of O2 we're going to need. All right, so here I go into my calculator. 2.864 divided by 114.23 times 25 divided by 2. Says here that we need 0.3134 moles of oxygen. So this is going to require 0.3134 moles of oxygen gas. We have to figure out how many liters that is. How many liters is this? Now, at this point, we've got 2 options. First of all, we can just set up a gas law equation. PV equals nRT. The pressure, well, it's here. It says that this is STP, so it is 1 atmosphere. Okay? The pressure is 1 atmosphere. The temperature is 273 Kelvin. The gas constant we use would be for atmospheres, since this is atmospheres. So the gas constant is going to be 0.0821. All right. We know the number of moles. The number of moles here is, well, we just solved for it, 0.3134. And we're trying to find the volume. How much volume does this gas take up? Well, You just divide both sides by 1, all right, which is like basically doing nothing. So the volume is equal to 0.3134 times 0.0821 times 273. So in the calculator it goes 0.3134 times 0.0821 times 273. And I get as an answer, the volume is equal to 7.024 liters. 7.024 liters. That's how much space, that's how much volume of oxygen you're going to need to burn. All right, so I'm going to go to my worksheet here, and I'm going to type in 7.024. Yay, liters! I did it. Now listen, there is another simpler way to solve this problem, all right? And it has to do with the fact that you were expressly told that this gas was at standard temperature and pressure. That this gas, this 0.3134 moles of oxygen, was at standard temperature and pressure. Well, guess what? We've already done a problem with standard temperature and pressure all the way up at the top. And what we learned was this. Under standard temperature and pressure, 1 mole of gas is 22.4 liters. Under standard temperature and pressure, 1 mole of gas takes up 22.4 liters. So, we can use that conversion to make our job easier. All right? 22.4 liters is equal to 1 mole of gas. So we can use this for a little bit of conversion. All right, here we go. 0.3134 moles times 22.4 liters for every mole of gas. And what do we get? What do we get? Here we go. 0.3134 times 22.4. We get 7.02. Boom! The same deal. So this is something that we talked about in class and can serve as a shortcut for you. And it is this. When you see STP mentioned, all right, you don't need to use the ideal gas law equation, all right? You don't have to use it. When you see standard temperature and pressure, what you know is that when you're going from liters into moles, you can divide by 22.4. If you're going from moles into liters, you'll multiply by 22.4. Again, this only works under STP. If you have any other type of gas condition, you will need to do the full PV-nRT equation. I hope this helped. Good luck.